Institute of Astrophysics, and Maheshwar Maji, who's on the faculty in the University of Goa, and Subrata Mukherjee here at IISc. So in fact, I mean, I'll sort of go a little bit again of the introduction, which Krishnendu already spoke about, so I apologize for the fact that some of this will be a repeat. So what I want to start with is just thinking about what happens to strongly correlated bosons, okay? And in particular, understanding just the Mott transition of bosons moving on a lattice where you have some hopping, some chemical potential that tunes the density, and some on-site repulsion that can be large and positive, for instance. And it's well known from the work of Fischer, Weichmann, Greenstein, Fischer, and a number of others who have already been referred to, that this model actually supports two phases in the phase diagram. So the phase diagram as a function of chemical potential and as a function of interactions, or T over J over V, but it's really T over U in this notation, sorry about that. Supports two phases, one which is a superfluid of delocalized bosons, and another which is an insulating phase where the boson number gets locked to an integer value at every site. Okay? And so this model was proposed early on in the context of people thinking about superfluid helium moving in porous media like Vicor and so on. But in fact, a very beautiful realization of this model, which was already pointed out in the previous talk, came from work on ultra-cold atomic gases. So these are pictures which you've seen many times already, early on also in the talk that Anton George gave as part of the lectures in the school, where one goes from a superfluid with a coherent momentum distribution which shows a peak at k equal to 0, evolving into a situation where you get sort of basically Bragg reflected spots which tell you the reciprocal lattice vectors of the lattice that you're imposing on the superfluid, eventually going to a Mott state where all kinds of all signature of coherence is eventually lost. There's another sort of interesting realization of closely related physics which comes from studies on Josephson junction arrays. Okay? So these are superconductors. This is just showing a picture of sort of these superconducting islands from the movie group. And you can sort of make them in different geometries, and they can do transport measurements on these. So as a function of temperature, you can measure resistance. And what one finds is, again, that there are two regimes in the transport. So if one looks at a regime where the Josephson coupling is large, so the Josephson coupling to charging energy ratio, so Josephson coupling is the analog of the boson hopping, right? So this tells you how easy it is for Cooper pairs to tunnel from one island to the other. The charging energy is the analog of the Hubbard repulsion, so it just tells you how much energy it costs if you try to change the occupation on an island by, let's say, adding an extra pair. And the ratio of these two can be varied by changing the size of these islands, right? So you can change the charging energy, or you could change the spacing and change Josephson coupling. Okay? And so by making different arrays, different samples, one can basically access the analog of T over U, which is the Josephson to charging energy ratio. And what one finds from transport measurements of the sort that's shown here from this group is that you find that if the Josephson coupling is large, you see evidence for superconducting transport where the resistance dives down. Whereas if you are, as you go to low temperature, whereas if you are in the regime where the charging energy is large, so that EJ over EC is small, you find that the transport has this like activated form or some form of insulating transport at low temperature. And in this limit, one can really think of this as being analogous to the Hubbard model, except that typically the charge on each island will be a large number. It won't be like one boson per site or like one Cooper pair per island, but you'll have a large number of Cooper pairs per island. And so you will be sort of in the regime where in terms of these Mott loads that I'm drawing there, you're sort of somewhere up there where there's a large number of particles. But the sort of thing that I really want to focus on in this talk is what happens if you take this thing and stick it in a magnetic field, and in particular I want to focus on a regime where I'm going to really stick in half a quantum of flux per plaquette of this array. Okay. So this is a system that has, if I think of it just bosons with charge E, hopping around on this array, then this is like having pi flux seen by these particles. And so if you go around one elementary loop or one elementary plaquette, you're going to pick up this Rhombomb phase of pi. Okay. And so now they can repeat these measurements. So you can do this. So this is just a later data from the same group, but basically comparing what happens in zero flux versus what happens if you have this half a flux quantum. And again, you see that the phenomena are sort of roughly similar, that you get superconducting states and insulating states as you tune this ratio. But the value at which you go from the superconducting to the insulating state is different when you turn on flux. So for instance, if I look at this plot here, the superconductor disappears when the charging energy is roughly 1.8 or something in units of the Josephson energy, whereas here it's already disappearing at about 1.1 or something. Right? So it just tells you that it's in fact much easier to destroy phase coherence and get locked into an insulating state when you have this kind of fluxes present in the system. Okay, so that's sort of the main message from this. So the y-axis, okay, so here, so here I'm not sure what they're, so I think it must be some measure of temperature, I think, because that's what they were doing here in this case. So it's some scaled temperature, and actually in this plot I'm not really sure what the tau is, but yeah, sorry. But I assume that it's some kind, this must be somehow scaled to temperature because this is like the normal state behavior.
So what is the temperature that measuring things like inside the gap?
So what is this scale here? Yeah, it's presumably the, right, so when you heat enough of these, presumably it will be like a conducting fluid. On the cold atom side, there's actually been a very beautiful recent progress which Krishnendu sort of very briefly alluded to, which comes from the fact that you can actually create analogs of magnetic fields for these neutral atomic particles. Right? So nominally you would, so one way that people have thought about to get magnetic fields into the system is to take a Bose gas and harmonic trap and really try and rotate it. And this rotation, as you can imagine, will produce vortices, and so it acts like the analog of a magnetic field. I mean, you can sort of do it more formally as well. But another way which it sort of goes back to this very beautiful proposal by Ian Spillman is one can actually use Raman transitions and spinor condensates to do something very similar. So very roughly what is shown here is the fact that there are three hyperfine levels in the problem, and what you're trying to do is you're trying to couple these different levels using lasers. And what you're getting is basically two photon sort of Raman transitions that couple these different states. But unlike in solids, here the Raman transition involves a change in energy, but also a change in momentum, because the momentum transfer is appreciable when one thinks about laser light and these atoms. The momentum transfer is actually appreciable. Okay, so you're looking at a sort of a finite wavelet analog of Raman transitions in solids, and so what is drawn here are basically parabolas depicting the dispersion of particles in, let's say, each of these hyperfine states, and they've just been, there's just a way of doing it that you shift them by the amount of momentum which is transferred when you couple it through this two-photon transition, right? So you just sort of shift them by hand so that one is shifted to the right and left, and that represents sort of the energy shift and the momentum kick that you will get if you do this two-photon process. Okay? And now if you actually put in this coupling, this is like having some off-diagonal sort of entries in the matrix, this 3x3 matrix that's going to describe this, and what you're going to get is some new dispersion obtained by coupling these three gray dispersions here. These three parabolic dispersions will mix and give you some new effective dispersions. And the main thing is that if one focuses on, let's say, the lowest dispersing band here, its minimum is basically shifted away from k equal to 0. Okay. And one can really think of that as if one has applied a vector potential, because after all the effect of a vector potential is to send P to P minus EA, and so you can view this as having started with a particle which had some P square over 2m, but now its dispersion has become P minus EA whole square by 2m, and A is something that's proportional to sort of the amount of the laser intensity and so on. Okay? So you sort of put in some kick there. And now you can ask, well, I can go one step further. This is like a uniform vector potential, but one can modulate this vector potential as a function of position and generate the analogs of magnetic field. So they've done this very beautiful experiment where they've shown that doing this kind of a process and imaging the condensate actually gives rise to these dark spots which correspond to vortices, and the counting sort of works out right, that if you count the amount of flux that you put in and sort of count the number of vortices, then you sort of see that that's a reasonable description. So in fact this development actually is very exciting, because in fact it sort of leads us to the prospect of actually getting very interesting states of bosonic, like bosonic quantum Hall liquids, or if you put this on a lattice, maybe like lattice versions of the quantum Hall problem. Okay. There have been other developments which are sort of related to what I mentioned earlier, but these are sort of done differently. In fact, I'm not going to touch upon how this is done. I've not sort of digested it carefully enough, but you can sort of take bosons. So this is sort of work where you imagine making a lattice by taking tubes, one-dimensional tubes, and now you form an array of these tubes. Okay, and you can form, for instance, and what they've done here is form a triangular array of these tubes. Okay, so if you take a cross section, it will look like a triangular lattice, but really these are extended objects in the third direction. And if the bosons were to hop around in, if the bosons in these different tubes, you have sort of a large population of bosons, and you can really think of this as a very classical state of the problem. Okay, so basically you can think of this as a condensate which has some phase degree of freedom. Okay, and now depending on how these tubes couple to each other, these phases are going to lock in some fashion. So for instance, if you just take the ordinary Josephson tunneling between these, which prefers all the phases to align, you're going to get a ferromagnet if you look at these phases, but they can actually arrange for the phases to actually acquire get more complicated looking patterns which correspond to, for instance, an antiferromagnetic coupling between these different tubes. Okay. And so you can realize, so you can think of this as, if you think of the ferromagnet as a case where bosons are hopping around and aligning, then in fact the case it's like an antiferromagnet is as if you put in a flux which frustrates this boson hopping and gives you this sort of analogs of the 120-degree state on the triangular lattice. One can do, more recently there's work by from Emmanuel Bloch's group where they've actually managed to achieve fairly large staggered fluxes. So imagine I take flux phi on one sublattice of a square lattice and flux minus phi on the adjacent plaquette, then in fact they've been able to get schemes where you can get fairly large values of these staggered fluxes. And again, going back to the thing I was talking about earlier, is if the flux is pi, in fact you don't care how you realize this, whether you realize this using these kind of schemes or whether you realize it as a staggered flux is really irrelevant for this for the case of pi flux. Okay, so what I'm going to imagine is that there is some way that these bosonic atoms have this kind of frustrated couplings which correspond to having fluxes here, and really ask what is the physics of the problem when you have this half a flux quantum and you turn on repulsive Hubbard interactions. Okay. So let's actually begin with the weakly correlated state, which is kind of easy to understand. Okay. So let me take, for instance, a simple case where I just have a two-leg ladder, right? So you have two one-dimensional things, and then you have some coupling between these two chains. And if one just looks at the band structure of this problem, which is what you would do if you had non-interacting particles, it turns out that the band structure exhibits two bands. Okay, so this is sort of like the Hofstadter problem, which I think we mentioned in Vijay Shenoy's lectures during the school. So this is like a Hofstadter problem where you just have you have just pi flux through each plaquette, and so you have two bands, and the lowest band has two degenerate minima, right? So for the particular gauge choice that I've made here, one of these minima sits at k equal to 0 and the other sits at k equal to pi. Okay. And now when I was using the word frustration, that's really because now the bosons really don't know how to condense, right? So imagine I had no interactions at all. You could put all the particles here, or you could put all of them there, or you could put some combination of here, some there, and so on. And it turns out that, and I'll sort of come to this in the next slide, it turns out that what happens when you turn on a small repulsive interaction, so you're sort of in the weakly correlated state, is in fact the state that you condense into is a macroscopic state where you macroscopically occupy a linear superposition of these two minima. Okay. And it turns out that the resultant state actually breaks time reversal and translational symmetries, and so for example for the ladder, it turns out that the ground state actually spontaneously generates currents of the sort where you have, let's say clockwise currents and counterclockwise currents which alternate as you go along the ladder. Or if you look at the square lattice, then again it's this thing like a checkerboard pattern of staggered currents. Okay. And in fact, there are a number of people here, including Krishnendu, who sort of looked at this problem at some length. One can sort of get some intuition for this by looking at some kind of a Landau-like description where you say, look, I'm going to think of these two minima as two bosonic modes and try to write down some kind of a like a free energy functional that looks at the like having a complex field that tells you whether bosons want to condense here or there into some linear combination. And in terms of the Landau theory, what you have is some quadratic level. This is like the non-interacting case where you don't really discriminate between this one or that one, which any linear combination is fine. But when you go to the quartic order, it turns out that there's one term that tells you that you want to create this linear superposition, which is like an umklapp term, which tells you that you could take two particles from here and put them there while conserving crystal momentum. And the sign of this is positive, which means that there's a certain relative phase between bosons here and there. Okay, so the state that you want to condense into is then a linear superposition of bosons at k equal to 0 plus or minus I times bosons at k equal to pi. Okay, so that's the linear combination that you want to condense into. So what we know then from the preceding couple of slides is that if you're in a weakly correlated state with pi flux, you have an unusual superfluid state which has these staggered loop currents. If you're in the very strongly correlated regime where the Mott Hubbard U is extremely large, then you clearly have a unique ground state where the number of particles, if you're at integer filling, is just pinned to be sort of that value at every side. And in fact, this, really speaking, this Mott localized ground state really doesn't care about fluxes in the sense that, as far as the ground state is concerned, you can just adiabatically turn off the flux, and you would not really, you wouldn't go through a phase transition as you do this. Okay. So the question then is, how does the ground state of the system evolve as you increase U? Okay. So if one looks at mean field theory, one can generalize the usual superfluid Mott insulator transition mean field theory, which has been discussed by Anton and for the students in the audience. But what happens if one generalizes that? So let's say I do this for zero flux. There's some superfluid to Mott insulator transition, and you find a quantum critical point that separates these. If you're at f equal to half, which is half a flux quantum per plaquette, you can repeat the same thing, sort of allowing for the fact that there's a time reversal symmetry broken superfluid, and basically you find that you again get a single continuous phase transition between the superfluid and this Mott transition. And the main thing is that the transition happens at a smaller value of U. Okay, if you do the mean field theory, and that's sort of qualitatively consistent with this experiments on Josephson junction arrays. So this is not something new that we have done. This is sort of known from earlier work by various people. So in fact, I'm just quoting a recent example of this stuff done in the context of cold atoms in 2008, but there's sort of work going back to Josephson junction arrays and so on, where people have looked at this in mean field theory. Okay? But really, if one thinks about this, the question is, if you look at the superfluid now, you say that, look, really it's it's not as simple as this problem here, because this superfluid actually breaks two different symmetries, right? So you've broken the U1, or at least you have Pauli order if you're in one dimension, but there is a U1 symmetry that's is broken or has Pauli order, where there is also a second one here, which is the breaking of time reversal associated with the fact that you have these staggered loop currents. Okay? So there are two different current patterns, and you have to spontaneously choose one of them. And so if this undergoes a single transition, it's kind of unusual, because there are two of these order parameters, the currents and the U1, which both have to disappear at this critical point. Okay? And it would be an unusual sort of example if that were true. And so it's kind of an interesting problem to look at anyway. Okay. So what we've done is sort of looked, and from the point of view of doing some concrete calculations, actually we decided to look at just a numerical study of the ladder problem. And so what we have is a two-leg ladder where you have two chains which are labeled, the bosons are labeled by A and B. And you have various terms in this Hamiltonian, which includes intra-chain hopping, where the bosons hop along these chains. There's inter-chain hopping, which is this perpendicular bonds, and finally there is the Hubbard repulsion. Okay. And so what we want to sort of jumped ahead there. So what happens if we increase U over T at a fixed hopping, and if you do the mean field theory, which I alluded to earlier, you can sort of write down some results for the critical, for the phase boundary in this of these Mott lobes. And for instance, if one looks at the pi flux to zero flux, what is the critical value of U, it turns out that you can show that this thing has some simple, relation to this T and T perpendicular, and turns out that's less than 1. Okay, so this is what I was referring to. But what we want to do is to go beyond mean field theory, and we'll use two different numerical approaches. One is to sort of map this problem onto a 1 plus 1 dimensional, frustrated classical problem. So think of these ladders, and you're going to stack these ladders in the imaginary time direction. And that you can sort of simulate using just classical Monte Carlo methods. And the other, which has been looked at, is basically to just simulate the ladder Hubbard model for bosons directly, but just at a filling of one boson per site, on average, doing a density matrix normalization group methods. So let me turn to sort of what we get for the results from each of these. Okay. So if you look at the classical model, what is it? It's basically, this is the ladder that I was drawing earlier, and if you want to do the quantum to classical mapping, you're going to sort of stack these ladders in the imaginary time direction. And so the model that you end up with, the classical model, looks something like this, where you have Josephson couplings like XY. So they're like an XY model with some couplings, and the couplings are in the space direction, which is the lattice. This ladder directions are basically like the boson hopping, right? So they are the hoppings that you start with, and in the imaginary time direction, they are like the inverse of the interaction U. Okay. And so if you want to look at the vanishing of superfluidity, so what do you have? You have a superfluid that eventually should become a Mott insulator. Okay, so you have to track how the superfluid density vanishes, and so what we've looked at is a computation of the helicity modulus, okay, which is like the superfluid density, and as a function of increasing 1 over j tau, which is like increasing U in the quantum problem, there is sort of, nothing much happens, and then there's this precipitous drop of the helicity modulus, which becomes sharper and sharper as you go to larger and larger system sizes. Okay. And so if you realize that you're in sort of in a quasi one-dimensional limit with this ladder, it sort of looks as if one might be undergoing a Berinsky-Koslitz-Thouless transition, where you expect, in fact, that this helicity modulus will jump from a finite to zero value at some critical point. Transition for these currents. Okay. So to summarize then, it turns out that if we look at what I just did and plot the 2 points, right? You have a Koslitz-Thouless point and an Ising phase transition, right? And if one can therefore take slice, so what is basically said is you fix J perpendicular or T perpendicular over T and take one cut, then you get sort of the data of the sort I showed. But you can sort of now repeat this at different values of the interchain coupling, and we find that quite consistently over a wide range of such hoppings, the superfluid goes into the Mott transition via two transitions, and there is an intermediate Mott insulator phase which actually retains staggered currents. Okay, so this is a costless transition where superfluidity vanishes, and later, once superfluidity has vanished, the current order vanishes at a larger value of U or a smaller value of J tau. Okay, so this is an interesting state where you have a paramagnetic state. For the spin model, it's a paramagnetic state which retains some memory of this vorticity that was present in the ground state of the superfluid. So we also done a DMRG study of the Bose-Hubbard ladder. And in order to, so here we have to look at slightly different quantities. So if you look at, for instance, if you want to ask where the insulator appears in the system, it's actually useful to measure the charge gap. And if one finds the charge gap extrapolated thermodynamically, but basically it's zero in the superfluid and then takes off at some value of U over T. So it becomes, it's zero everywhere and then becomes non-zero beyond some critical value. Another way to detect this vanishing of superfluidity is to look at actually the momentum distribution itself, which was shown in some of these cold atom plots. And if you're in a superfluid, imagine you're in a Bose condensed superfluid, then this, the momentum distribution at k equal to 0 will scale with the system size. Okay, because you're in a Paolo ordered phase here in one dimension, it will scale as L to the power of some number which is less than 1. Okay. So if you have to actually check whether this is a BKT transition, one useful thing to do is to plot the momentum distribution at k equal to 0 scaled by L to the -3/4. Okay. And the crossing of these curves again tells you that if there is a costless Thouless transition, then this is where you're going to locate it. Okay. That's because at the KT transition, the real space correlations decay is 1 over x to the 1 over distance to the 1/4. Okay. And remarkably, it turns out that the crossing point that one gets from this momentum distribution calculation basically coincides with the onset of the charge gap. Okay. So this tells you again that you're undergoing a transition from a superfluid into an insulator at this critical point, and that seems consistent with what one expects for a BKT transition. Okay. To detect the current order, we can look directly at the structure factor instead of looking at binder cumulants, and again we find that if you sort of look at the structure factor scaled appropriately with beta and mu chosen to be the Ising order parameter and correlation length exponents, again we find that there's a crossing point, and one can scale this axis as well to basically get a complete collapse of the data. Okay. So again what we find from the DMRG then is basically two transitions which we located in this manner, and it turns out that these two transitions do not coincide, and again the order of the transitions is the same, namely that if you increase U over T in this model, so this is directly just the Hubbard model U over T, one finds that the system exits from a superfluid into an insulator, but the insulator basically retains this vorticity correlations in the problem. Okay, so what I want to turn to in the next, I don't know how many time I have, but few minutes, 10 minutes, okay. So what I want to turn to, I'll just finish early, but what I want to turn to is just some cartoon sort of pictures for this chiral Mott insulator ground state. Okay, so let's think of what the chiral superfluid is. Okay, so the chiral superfluid, as I mentioned already, contains currents that are circulating, but they have opposite circulation on adjacent plaquettes, and so you should, so very roughly one can sort of rationalize this by saying, look, if I have frustration, then the way the system is going to sort of solve the problem locally on a plaquette is to either induce a vortex or an anti-vortex. Okay, so you're going to break time reversal in some fashion on a plaquette. And now if you want to ask how these things are going to stack when you form a lattice, then if you recognize that the vortex-vortex interaction is repulsive, then the simple thing is to say I'm going to form an antiferromagnetic stacking of this vortex, anti-vortex, that I've generated a whole bunch of vortices, anti-vortices. I want an antiferromagnetic stacking of these. So this is really like an antiferromagnetic crystal, okay, in terms of the vortex picture. Okay. If you think of the regular Mott insulator, it is well known from work going back to various people, and so they sort of work in two-dimensional system, but lecture we'll also work on 1D, where you should really think of this as some kind of vortex superfluid, or in this case where quantum phase slips are basically proliferated if you're sort of in this one-dimensional quasi 1D limit. And so this is really like a vortex superfluid. And so if one thinks about this, the intermediate state then is very naturally thought of as a supersolid of vortices. Okay, so you have, imagine I have vacancies or interstitials of vortices, and they're dilute and somehow they're delocalized. Then that's enough to kill sort of the phase order present in the superfluid, but it's not enough to destroy the crystal order present in the background. Okay, so that's sort of the cartoon picture, and we are sort of working to making this slightly more concrete, picture slightly more concrete. Another interesting cartoon picture actually emerges if you start from the conventional Mott insulator and sort of look at the excitations which Krishnendu mentioned in the previous talk. Namely, one has in the Mott insulator, right, conventional Mott insulator, you would have gapped particles which are sort of doubly occupied sites where you added an extra particle that costs some energy. You could also have holes where you removed some particles, and these are basically gapped excitations in the system. And if you allow for these things to actually hop around, then basically you will form the analogs of dispersing bands like in a semiconductor, right? So there's some gap and then there is some dispersion. Okay. So if you think about what happens, what is different between a conventional Mott insulator with zero flux and a Mott insulator with flux, then the main difference is the fact that as these gapped excitations propagate, they are actually sensitive to the presence of this flux, right? So what you get is again two bands where the band, the sort of lowest energy band of these dispersing excitations has two minima, and again for the particular gauge box here it's sitting at k equal to 0 and pi. But one thing, so what we're trying to do now is to take this, the analog of the semiconductor, this Mott semiconductor, and basically decrease U, which means you're sort of trying to shrink the band gap of the semiconductor and trying to make it metallic, which will allow these bosons to condense, right? Once the energy becomes zero, the bosons will condense as we mentioned earlier talk. But one thing we know is in fact that before you metallize semiconductors, one can in the vicinity of that transition actually have exciton condensate. So you can form particle hole bound states and have them condense. And so in fact the chiral Mott insulator is most naturally thought of as, in this picture, as an indirect exciton condensate. So it's like an exciton, but it's just completely boson. So you think of, let's say, doubly occupied, so let me call these as particles. Okay, so these are gapped, like doublons or something, and these are holes, and these can have dispersions, and what you want is a state that breaks time reversal symmetry and breaks translational invariance. And so in fact the most natural is sort of, I'm skipping over the details here, but the most natural way to think of this is you take a particle like excitation sitting at one minimum and a hole like excitation sitting at the other minimum, because it's like a sort of a system where you have multiple values and you can form these indirect excitons. And so the chiral Mott insulator is really an indirect exciton condensate where particles and holes are individually gapped, so it's not a superfluid, but nevertheless these excitons are condensed, so you've broken some symmetry in the problem. So just take 1 minute and then okay. So another thing we've looked at is asking more directly, well, here is a phase that we've talked about, the chiral Mott insulator. Can I write down a cartoon wave function that describes the state? Okay, and so to do that we'll actually, oops. Is this powered right or? Okay. So if you imagine you want to write down a many-body boson wave function just in first quantized description, so you have some wave function that is a function of these n coordinates and it has to be symmetrized. And if you want to build in correlation, then you say, well, I'm going to take some mean field condensate wave function, and I'm going to build in interparticle correlations through some two-body Jastrow-like factors. Okay, so these just depend on the relative coordinates between pairs of particles, and so if you take this and you hit it with the Jastrow factor, you're building in correlations on top of a simple mean field state. Okay, and so what we can do, which we've done, is to take the mean field state to be just the ordinary chiral Bose condensed superfluid. So you say, well, I have these two minima, I'm going to create this superposition and put all the particles into that Bose condensed state, and in order to be able to describe a superfluid with linearly dispersing Goldstone modes, one actually has to see that this Jastrow factor has certain constraints. So in other words, if I take the Fourier transform of the Jastrow factor at small q, it turns out it has to go like 1 over q squared. Okay? And so if we pick this function appropriately, then it turns out you can describe a superfluid ground state. Okay. So what we've done now is to ask, well, so this should have been 1 over q if this was a superfluid, but imagine what you want to do is now you want to describe an insulator where there's a gap. Okay. Then it turns out you have to choose slightly more singular Jastrow factor. Okay. And this follows from a simple Feynman, like a single mode type argument where the excitation energy of states above the ground state within a single mode, if you look at density fluctuations, it scales like it scales like basically the inverse of this divided by it scales like q squared divided by the structure factor, and the structure factor is dictated by the behavior of the structure factor is governed by the behavior of this Jastrow function. Okay. So if you take the Jastrow function to go like 1 over q, the structure factor is linear in q at small q, and you get phonon-like excitations if you look at q squared divided by q squared divided by sq. But if you take the Jastrow function to be more singular, you get a structure factor that is in fact goes like q squared at small q, and you would expect a gapped ground state. Okay. And so in order to check that, we've also taken this mean field state, hit it with this Jastrow factor, and actually computed what the boson-boson correlations are. So if you look at the Green's function, you expect that if there is off-diagonal long-range order in the superfluid, this thing should saturate, but we find consistent with what I just mentioned that in fact it decays exponentially in the state. Okay. So what we have is a simple sort of cartoon wave function for this Chiral Mott insulator ground state. And so going to this picture here that I mentioned earlier about these two modes at k equal to 0 and k equal to pi coming with a relative phase pi by 2 and some global phase associated with the sort of U1 symmetry breaking, really what we're doing is we're using this Jastrow factor to basically, it's like something that builds in number correlations and sort of disorders this phase variable here, but maintains the relative phase to be plus minus pi by 2. So, okay, I've picked one choice for this thing. I've picked pi by 2 instead of minus pi by 2, but basically that's the. So what about experiments? So one can realize these kinds of things that I mentioned already in Josephson junction arrays, and it turns out quite reasonable that if you could get the kinds of systems that one has looked at, the kinds of system sizes, the kinds of geometry one has looked at. In fact, one can see that one should be able to see something that's an insulator if you look at transport, but has these kind of staggered magnetic fields generated by these staggered currents. The sort of one complication, however, is that given that this is a small window, you want to be able to sort of do some experiment where you can tune this ratio smoothly in order to be able to access points that lie inside this Chiral Mott insulator state. And it's not clear exactly how one would sort of set that up, but it's it's a challenging thing. But at least this is one prediction. A second is if one looks at the cold atom realization, if you are in the Chiral Mott insulator ground state and you look at the momentum distribution in all, the superfluid Mott or Chiral Mott, it turns out the momentum distribution always has two peaks at k equal to 0 and pi, which reflect the existence of these two low energy modes. But in the Chiral Mott insulator, one expects a residual sort of phase coherence that should be present between these modes at k equal to 0 and pi, which is this pi by 2 relative phase that I mentioned earlier. Okay. So just to conclude, what we've shown from careful numerical work on the Hubbard model on the ladder is that in fact the phase diagram of the system is interesting, and it supports an sort of an intermediate Mott insulator phase with staggered currents, and then we've sort of discussed some simple pictures for the Chiral Mott insulator, and looking beyond. We're sort of working on trying to understand some of this in field theory and trying to look at some higher dimensional generalizations. So thank you for your attention.
So the coupling between chains is weak, or you still get this phase? like a phase diagram is functional coupling to
Yeah, so it's not, so we've not done sort of a whole range, okay? So in the vicinity of this point, so the smallest we've gone to is about 0.5, so I don't know what, I mean, okay, so you just drawn this here, but it could be that these two merge into a single, so that's not clear actually from numerics. So the other thing we're thinking was whether it will merge at large, okay, I don't know the answer at this point.
Yeah, I think that if the phase diagram is like this, and it doesn't merge, then maybe if you had a two-dimensional array with big coupling, it would
Yeah,
still
then it
be
will survive, yeah. So one thing, so we expect that the extent may go down as you couple them strongly, but meaning as you turn up the inter-ladder coupling, right, but otherwise it should survive because some gapped phase that should, or even here, right, so imagine, okay, so you're thinking of weakly coupled chains but forming a quasi one-dimension, but weakly coupled ladders will certainly survive, but you're right, yeah, I don't know about the 2D limit of this.
So regarding the detection of that phase in the cold atom context, you mentioned the extra weight in the N of K or Bragg scattering stuff. Can you think of other sort of smoking gun detection of this orbital current?
Yeah, actually I don't know of ways to detect currents directly. Yeah, I mean there have been some theoretical proposals that came up in the context of the fact, in the context of the experiment that I mentioned earlier, where people have seen these current states. But I think most of the time what people do is to use that to model N of K itself. So it's not. I don't think it's.
What happens if you do Bragg scattering with polarized light, for example?
I see, okay. I haven't, there may be a way actually. Yeah, we should chat after the talk. So the thing we were thinking of is actually taking the, so normally you do time of flight and then you take these two modes and you just measure the number, right? But on the other hand, if we claim that there is some residual phase, one thing to do is to sort of do time of flight but then let them re-interfere. So you sort of apply a Bragg pulse that tries to bring them back and see if there is interference. But it's probably harder.
So my question is related to numerics. Can you get ground state fidelity and ground state fidelity susceptibility using DMRG?
And it's some wave function overlap. So DMRG has access to wave functions. So I'm not an expert on DMRG. So you should ask Arya, who's somewhere in the audience. But I think it's possible because you have access to wave functions, and it should be possible.
So if you can access that, what do you expect? Can you detect the BKT transition using ground state fidelity and fidelity susceptibility?
Maybe, okay. I haven't thought about fidelity susceptibility at KT transitions.
Okay.
Sorry.
Thank you.
Any other questions?
Okay, if there are no other questions, let's thank Arun again. There's a change in the schedule, so there's going to be one more talk in this session before we break for tea.
Because there are some mismatch between, I apologize, the mismatch between